Today we will see Kirchhoff's voltage law and Kirchhoff's current law. Let's start with Kirchhoff's voltage law. Kirchhoff's voltage law or KVL states that the algebraic sum of voltages around a closed loop will be 0 for a lumped electric circuit. For example, consider the circuit shown here. The voltage is V and it is connected across three resistors R1, R2 and R3 connected in series. Now since there is only one source, the source will be delivering power and therefore the direction of current will be from plus to minus, that is current will flow in the clockwise direction. And the current entering terminal of resistor will be positive with respect to the other terminal. So we have marked here V1, V2 and V3 with respect to the clockwise current flowing through the circuit. So if we apply KVL, we will get V minus V1 minus V2 minus V3 equal to 0. The reason is with reference to V1 is the connection is plus plus, so we have to take the difference. So the source V is taken as the reference and from that V we have to compare the polarity of each element. So if it is plus plus, you will have to take the difference. Hence we will get V minus V1 minus V2 minus V3 equal to 0, or we can write it as V equal to V1 plus V2 plus V equal to V1 plus V2 plus V3, or we can write it as I into R1 plus I into R2 plus I into R3. So this is Kirchhoff's voltage law. Now we will see Kirchhoff's current law. Kirchhoff's current law states that the algebraic sum of current at any junction is 0. That is, when you consider a node, the sum of current entering will be equal to sum of current leaving. Consider the circuit as an example. Here there is one junction to which three branches are connected, R1, R2 and R3, and I have marked the direction of current. I1 is flowing into the junction, I2 is also flowing into the junction and I3 is flowing outward. So the current entering the junction is I1 and I2 and leaving is I3. So by applying KCL, you will get I1 plus I2 is equal to I3. Total current entering is equal to total current leaving. This is Kirchhoff's current law. Today we'll move on to the most important topic of our first module, which is node analysis. As I said earlier, there are two ways in which you can analyze a network, two basic ways. The first one is node analysis and the second is mesh analysis. Node analysis is based on Kirchhoff's current law. Now these are the basic steps to perform node analysis. The very first step is to identify the number of nodes. Now we call a point as the node if it is an interjunction of two or more branches. So any junction where there are two or more branches can be called as a node. So the first step is you have to identify the nodes in the given circuit. Then second is assign node voltages with reference to ground node. So first identify the nodes and then assign voltages. By assign voltages we mean you simply name them by V1, V2, V3, etc. And when you assign a node as V1, it means the voltage at the node is V1 with respect to the ground node. The ground node is always taken as 0 volt. So V1 will have a plus polarity with reference to the ground node. The third point is, now this is actually not a rule but a convention which can be followed. You can proceed in two ways. One is you can look at the actual direction of current flow and assign that direction, or you can assume that current is leaving the node. Okay, so what we follow here, or what I think is easier, is you blindly assign that current is leaving the node, except if the direction is arbitrarily given in the question. Okay, so you identify a node, you assign a voltage to it, and then you assume that current is leaving the node. And finally, after assigning node voltages and marking the direction, you can use Kirchhoff's current law and then apply Ohm's law equations. Okay, so these are the steps. I'll explain once more. The first thing you have to do is you have to identify the nodes in the given circuit, assign node voltages, assume that current is leaving the node, and finally apply KCL. Now, to get a better understanding of this, we'll consider a circuit. Now, consider this circuit. Now, this circuit contains all the network elements which we have learned. It has both current source as well as voltage source. It has resistor, inductor and capacitor. So, best example to explain node analysis. You can draw the circuit in your notebook. Now, the first step is, as I've said earlier, we have to find the nodes, identify the nodes. So, when we observe this, we'll see that there are 2 points where 2 or more branches meet, so that you are marked by putting a dot. So, there are 2 nodes. I have marked it as black dots, and you can assign voltages to the node. So since there are 2 nodes, I am assigning it as V1 and V2. The first node voltage is marked as V1 and the second node voltage is marked as V2. Okay, now we'll start with node 1. Now when you focus on node 1, we'll see that there are 3 branches associated with that particular node, right? V1 to the node, first node, there are 3 branches. So a general convention is we are assuming that current is leaving the node unless direction is given. What I mean is, if a current source is present in the branch, you take the direction of current source as given in the question itself. So here a current source is given and the direction is flowing into the node. So you keep I1 as entering the node. And other 2 branches you assume it as leaving the node. Is it clear? Our general assumption is, after identifying the node, we assume that current is leaving the node. All the currents, we assume that it is leaving, except one condition is the direction is given in the question. It is marked already in the question as it is entering, then you will have to keep it as such. Or if there is a current source, you have to mark the actual direction. So only in these 2 cases we take the actual direction. One is, if a current source is present, you will have to take the direction of current source as such. Second is, in the question the direction is given. In all other cases we assume that current is leaving the node. So here I1 is taken as entering the node and I2 and I3 are taken as leaving the node. So when you write the node equation for node 1, it will be I1 equal to I2 plus I3. Now we can write down what is I1, I2 and I3. I1 is the current source itself, so it is I of t. Now what is I2? I2 is current flowing through the resistor R1. If V1 is the voltage across it and R1 is the value of resistance, then I2 will be V1 by R1. I2 is V1 by R1, current flowing through resistor. What about I3? I3 is current flowing through capacitor. What is its equation? It is current flowing through capacitor. The general equation is 1 by C. It is not 1 by C, it is C dV by dt. Right. So here there are two voltages. So it will be C into d by dt of current flowing through capacitor. The general equation is C into dV by dt. Here there are two potentials, V1 and V2, and we have assumed that current is flowing from V1 to V2. So current will always flow from higher potential to lower potential. So you should take it as V1 minus V2. So the equation will be C into d by dt of V1 minus V2. So the equation for node 1 will be I1 equal to I2 plus I3. I1 is I of t. I2 is V1 by R1. I3 is C into d by dt of V1 minus V2. Is this clear? Analysis of node 1. Now we'll move on to node 2. For analysis of node 2, you take the second node. It is already assigned as V2. Now here there are no current sources in the branch. So you can assume that current is leaving the node. All the three branches, the current is leaving. So you take it as that I4 is leaving, I5 is leaving, and I6 is leaving. See, analysis of nodes are independent. That means, see, in node 1 we have taken that I3 is flowing towards V2, right? When you analyzed node 1, you have taken the direction of I3 as flowing from V1 to V2. And when we are analyzing node 2, it is taken as flowing from V2 to V1. There is no issue in that. Each node is analyzed independently. You are analyzing the node, you are identifying the node and assume that current is leaving the node. So you can take I4 as moving from V2 to V1. There is no problem in that. So what will be the node equation here? With respect to second node, it will be all are leaving, right? So you can take it as I4 plus I5 plus I6 equal to 0. That is, sum of current entering is equal to sum of current leaving. Here there is nothing entering, so that is 0. And sum of leaving is I4 plus I5 plus I6. Now, we will have to write down what is I4, I5 and I6. I4, similar to what we have done for node 1, it is current flowing through capacitor. So, it will be C into d by dt of V1 minus V2. I have wrongly written here. It is not 1 by C, it is C. Please correct it. This one is C. Just a minute, I'll correct it. Okay. So the equation is I4 is C into d by dt of V2 minus V1. Now what about I5? I5 is current flowing through inductor. Current flowing through inductor is 1 by L integral V dt. We have already learned the basic equation. So it will be 1 by L integral, here the voltage is V2. So integral V2 dt. Plus, now to analyze the third branch, that is I6, there is a potential, there is a source V of t. And we have assumed that current is flowing from V2 to V of t. So you have to take it as V2 minus V of t divided by the total resistance R2 plus R3. See the position of R3, whether below V of t or above V of t is irrelevant. Wherever it is, you can take it as sum, R2 plus R3. It can be anywhere in the given branch. The position of it with respect to V of t is irrelevant. So I6 will be V by R. V here is difference, potential difference. So it will be V2 minus V of t by R2 plus R3. So this is the equation for the second node. So this is how you analyze a circuit using node analysis. It's pretty basics. If you clearly understand the steps and follow it, there is no confusion. I'll explain the steps once more. The first step is we have to identify the nodes in the given circuit. Second is assign voltages to the nodes. Third is you assume that current is leaving the node always, except for two conditions. One is the direction is given in the question or there is a current source. In both these two cases, you have to follow that. Then finally, write down the KCL equation and then the expanded equation. So this is node analysis. Before starting doing problems, I would like to bring your attention to certain specific cases. Now consider these two circuits. Here in the first circuit, you have a current source in series with a resistor 1 ohm. Then what will be current flowing through the 1 ohm? When you connect a current source in series with 1 ohm, definitely the current flowing through 1 ohm will be 2 ampere. Same way, in the second case, I am connecting a 100 ohm to this 2 ampere current source. So what will be current flowing through 100 ohm? It will also be 2 ampere. That means whatever value of resistor you connect in series with current source, current flowing through that resistor will be same as the value of current source. Right. So the value of resistance is insignificant there. Even if you remove the resistor and replace it by a short circuit, again current flowing through that path will be 2 ampere. So any resistance which come in series with a current source can be neglected. Is it clear? So you can just remove the 1 ohm or the 100 ohm and simply replace it by a short circuit. So all elements which come in series with a current source can be neglected because its value is insignificant. Whatever be the value of element you are connecting in series with current source, the same current will be flowing through it. I have taken two examples. One is 1 ohm and the other is 100 ohm. And we have seen that in both the cases, current flowing through it is 2 ampere. So the point to be noted is, any resistor connected in series with a current source is insignificant and you can remove it from the circuit. Now consider the next case. Here in the first case I am connecting a voltage source in parallel to 2 ohm. Okay. So what will be the voltage developed across the terminal A and B? It's parallel connection. There is no series component. So there won't be any drop in between. All parallel points will have the same voltage. Therefore, voltage at AB will be 10 volt. Similarly, in the second case, I am connecting two branches in parallel, 2 ohm and 100 ohm. Again, the voltage across AB will be 10 volt itself because all the points are in parallel. So, all parallel points will have the same voltage. That means there is no significance for the value of 2 or 100. Whatever be the value of elements connected in parallel, it is immaterial and the voltage across AB will always remain the same as that of the source. Okay, but if there is any series element in between, suppose there is some resistor here, okay, some resistor here, then voltage across AB is not 10 volt. It will depend upon the drop across this and the remaining elements. But as long as there are no series elements in between, here or here, the voltage across VAB will remain 10 volt itself. That is, any resistor connected in parallel to a voltage source is insignificant and can be removed. Is it clear? Now we'll see another case. Now consider this case. You have a current source across which I have shown 3 branches. One is a resistor of 1 ohm, a capacitor of 1 farad and a short circuit. And I have marked the currents as I1, I2 and I3. Now can you say what is the current flowing through I1? What is the value of I2 and I3? Here we see that there is a 0 resistance path and 2 resistance path, right? And you are connecting a 2 ampere across it. In such scenario, the complete current will flow through the short circuit path. Why? Because there is no resistance. Okay, so the complete 2 ampere will flow through the short circuit path and hence I3 will be 2 ampere and I1 and I2 will be 0. So whatever be the number of parallel branches, if there is a short circuit branch in parallel to it, then current flowing through all the other parallel branches will be 0. Because when you apply current division rule, what happens is there won't be any split up of the current because the current sees a 0 resistance path. So there won't be any splitting of the current. Complete current will flow through the 0 resistance path. So here I1 will be 0, I2 will be 0 and I3 will be the value which the current source provide. Here it is 2 ampere. So these are the 3 points which I would like to stress on. The first one is any element which come in series with current source is immaterial. Second, any element which come in parallel to a current source, parallel to a voltage source is immaterial. And third, any element which come in parallel to short circuit is immaterial. Okay, all these points you may come across when solving problems.